In this lecture, we're going to talk about the inverse of a matrix. Now, whenever we're talking about matrices, what are we really talking about? Well, we're talking about linear transformations, right? So matrices encode linear transformations. And so really the question that we're going to ask today, this will be sort of our motivating question, is when is a linear transformation reversible? Okay, and we'll talk about exactly what we mean by that. Okay, actually, yeah, let's jump into some examples right away. So I'll give you a linear transformation. So consider the linear transformation and let's go from, let's do one that we've seen before actually. So this will be the transformation from R3 to R2. And how will I tell you what this linear transformation is? I'll give you its matrix. Okay, so it's given by the matrix A, I'll call it. And so this is going to look like this, 1, 0, 0, 0, 1, 0. Okay. Before I tell you the question, this matrix looks simple enough, or maybe we can just understand exactly what this is doing. Okay, so what is this doing? Well, yes, it's going from R3 to R2, and it's sending our first basic vector of R3 to 1, 0. Okay, so let's try to draw this. So I'm going to draw a three-dimensional space. And so it's sending, and here's two-dimensional space over here. So it's sending 1, 0, 0 to 1, 0. It's sending 0, 1, 0 to 0, 1. And then it's sending my sort of z vector, 0, 0, 1. It's just sending out to 0, 0. So what is this doing? It's sort of flattening this three-dimensional space. So everything on this xy axis down here is just staying where it is. Okay. I'm drawing it from a slightly different angle, but that's okay. But then everything up here on the z-axis is just getting, for example, this point, or even if I had a plane up here, what's happening to that plane? See, this is actually saying the z-axis is just getting pushed down here to onto this plane. Right? So this actually also just ends up mapping to this same plane here. Okay. Okay, so we kind of understand what's going on here. We have a visual picture of it. Let me ask a question now. So, is there a transformation that reverses this one? So what do I mean by that? Is there a transformation, let's call it S, and this one will go from this space to that space. So we'll go from R2 to R3. That sort of undoes this transformation T. Well, what do I mean by that? Such that if I do T and then S, I just get back exactly what I started with. Okay, so I get the identity transformation on R3. Okay, so I'm saying, can I find an S so that if I compose it with T, it basically does nothing? Okay. Well, the answer is no, because see what's happening is I'm collapsing all of the points on this z-axis down to just this one point, 0, 0. So there's no way I can reverse that, right? I can't take that one point and then somehow use this transformation S to map that back to the entire z-axis. That's just not possible. So the answer is no. Why? Well, because this transformation T is not one-to-one. That's the key. So it's not one-to-one. It's not one-to-one. And again, here's sort of the picture to have for this. So if I have a transformation that's not one-to-one, okay, it's going to look like this. It will actually map 2 points, or in this case, infinitely many points, onto one point. So here's my domain, here's my codomain. And then if I want to reverse this, then well, where should I send this point? Okay, so let's draw a question mark, right? Because we don't know where to send that point. If we send it to this point here, well then look what happens to this point. It goes there and then up there, right? So that's not the identity, right? This is not getting mapped back to itself. It's getting mapped to a different point, okay? Great, yeah, so we cannot find an S, so we can do T composed with S and just get back to where we started with. Not possible in this case. Let me do another example. Now let's consider a different linear transformation. Also call it T. Let's go from R2 to R3 this time. Okay, so we're including a smaller space into a bigger space. I mean, this transformation might also involve some collapsing, but I'll have to tell you exactly what it is. So it's given by this matrix. Okay, so 1, 0, 0, and then 0, 1, 0. Okay, what is this doing? Well, again, I have my two-dimensional space here. And then the vector 1, 0 is getting sent to, notice I'm going to three-dimensional space, so I have to draw a three-dimensional space here. But 1, 0 is just getting sent to 1, 0, 0. And then 0, 1 is getting sent to 0, 1, 0. Okay, so all that's happening is I'm sort of including the plane into three-dimensional space. But there's this z-axis here, right? There's this third dimension. And nothing is mapping to 0, 0, 1, for example, right? I definitely cannot get the vector 0, 0, 1 in the image of this transformation. Okay. So again, here are my three directions. So same question. Is there an S going from in the other direction? So from R3 to back to R2. So here's my T. R3 back to R2 such that if I do T and then S, I get the identity. Okay. Well, sure, right? So yes, in this case. Actually, before I say that, there's another way to phrase this question. Let's phrase it in terms of matrices, right? So, i.e., is there a matrix? Here's my matrix A. So what are we asking? Is there a matrix B such that B times this matrix A I have equals, right? Because I'm doing A, then B. Okay, you have to get used to this opposite order, right? That is following the function notation, so it does make sense. Can I do A, then B, and get the identity matrix? Okay, so the identity matrix represents the transformation that just keeps every point where it is. Okay. And again, the answer is yes. We just sort of send this plane back, okay, to that plane. So how do I do that? Well, I have to say where I send the vector 1, 0, 0. Okay, I have to send that to 1, 0, just back to where it came from. And then I need to send the vector 0, 1, 0 to 0, 1. Oh, but wait a second. What do I do to this z-axis? 0, 0, 1. Where should I send that? It turns out it doesn't matter much, but let's just collapse that back down, kind of like this transformation here. Okay, and in fact, we see we get exactly that transformation. Yeah, so we can actually find a matrix, and you can check if you do B times A, you get the identity matrix. You get the 2 by 2 identity matrix. Okay. So we say that this matrix A has at least a left inverse. So A has a left inverse. There is a matrix you can multiply on the left to get the identity matrix. Okay? And again, that has the interpretation of doing A, then doing B. Right? Okay. Well, there's a little more to this story. Okay? Because as this example shows, we sort of cannot do this in the reverse direction. So let me draw the complete picture here. We have a map from R3 to R2, a linear transformation. There's my T. And we found a matrix S, or a linear transformation S, allows us to sort of do this in reverse and just get back exactly what we started with. Okay, every vector will map to itself, doing T, then S. Well, what if we started over, this should be R2, and this should be R3. Okay. What if we start in R3 instead? Okay. Can we do S and then T and then get back to where we started with? Okay, that's what it would mean for this transformation T to be truly invertible. Okay. So I'll write that. So this is the motivation for the definition of invertible transformation. This definition looks strange at first. Yeah, what if we start in R3? So I want to ask the question, is there an S, maybe the same S that we just found, such that if we do it in the other order, so we do S then T, is that going to be the identity transformation on R3? Okay, well, the answer is no. But what is it about this T that makes it so that we can't do S then T and get the identity? So why? In this case, it comes down to T not being onto. So it's because T is not onto. Okay, all these concepts, one-to-one, onto, invertible transformations, they're all interlinked. Okay, that's the thing about linear algebra, is everything is interconnected. So here's the problem. Okay, so let me draw a similar picture. So let's say I have my R2 over there and an R3. I mean, it's not a good picture of R2 or an R3, but just abstractly, this is what's happening. So let's say I have some transformation T that's not onto. Okay, so I'm missing something there. Well, what if I start at this point here that I'm missing? It has to map to something, right? But then whatever I map to, that cannot come back here because T is not onto. Okay, so there's no way I can start here, go there, and then go back there, and just end up exactly where I started. And again, that comes down to the fact that T is not onto. Okay, I would like to sort of map back to that point, but I can't, just because T does not let me. There are certain points that are not in the range of T. Okay. So what do we say? We say, so T, transformation T, this one was really nice. It did have a left inverse, but T does not have a right inverse. Okay. Well, I think it's time to define what we mean by an invertible transformation. Okay, and this is the motivation. So we say a transformation. So first I'm going to define this for transformation, and I'm going to immediately define it for matrices. It's the same concept. So a transformation from, let's say, Rm to Rn is invertible. Extremely important concept. If, okay, what do we want to have? We want to have both a left inverse and a right inverse in order to call it truly invertible. So if there exists some transformation S, so a transformation S, where is S going to start? Here, right? Rn, and it's going to go back to Rm, such that two things. Here's the first. If I do t and then s, that's what I just wrote. T then s, I get the identity. And that's the identity where? That's the identity on Rm, because I'm going here and then back. But I also want to be able to go the other way. So if I start from Rn, then go back to Rm, then use t to go back to Rn, I also want that to be the identity. This time it's the identity on Rn. Okay. So invertible sort of means I can reverse the transformation, but in both directions. Okay. Well, okay. Similarly, we can say this for matrices. So let's do that right away. So similarly, I'll just keep this on the screen. A matrix A, let's call it, is invertible. Let's just try to translate this definition, right? It's invertible if, so we can call either a transformation or a matrix invertible, if there exists another matrix, a matrix B, let's say, such that, well, what do we want? We want, if we do A and then B, A times B, that's doing the transformation sort of T and then the transformation S, we get the identity. What would the identity be in terms of matrices? What would be the identity matrix? Okay, and, they put an and here just to emphasize. You can't just choose one or the other. You need both of these things. And doing B then A gives me the identity. That's what I just wrote. And here, this matrix B, if I can find a matrix like this, and yeah, so if I can find a matrix like this, B is called the inverse of A. The inverse of A. And denoted, here's our notation, A inverse, like that. Okay, so that's the notation we use for the inverse matrix of A. Okay. So first thing we can say about transformation, we can actually say a lot more. So the first thing we're going to say is, so actually, for some transformation T to be invertible, well, it must be, we just reasoned through this on the other page, so it must be 1-to-1. If it's not 1-to-1, then we can't have a left inverse. But it also has to be onto. It has to be 1-to-1 and onto. Okay, these are necessary conditions for an inverse to exist for my transformation T. Well, let's think about that. So how can a transformation be both 1-to-1 and onto? Well, if M is less than N, okay, if I'm mapping from a lower dimensional space to a larger dimensional space, there's no way I can be onto, right? We proved that in the lecture about onto. Similarly, if I'm going from a larger dimensional space to a smaller dimensional space, there's no way it can be 1-to-1. There has to be some collapsing down, right? So the only way this is even possible. So the only way this might happen, sorry. The only way this is even possible is what? It's if M equals N. It's if I'm mapping from the same dimensional space to the same dimensional space. Okay. So what's the upshot here? And very, very important. We can only define matrix inverses. This is the only situation we can even talk about the inverse. So we can only define inverses for square matrices. Okay, if it's not squared, then it represents a transformation that either cannot be one-to-one or cannot be onto. Right? So we only, matrices should be grammatical here. Very important. Okay. So here's my first example. You should be able to answer this one immediately. Let's compute some inverses. So what's the inverse of this matrix? Alternatively, what's the inverse of the linear transformation given by this matrix? So how about 0, 1, 4, negative 1, 1, 0, and that'll be it. Okay, what's the inverse of that matrix? Well, what do we just say? We can only define it for square matrices. So this is not defined. It's a bad question. It's a bad question. It's such a bad question, I'm going to put a line through it because this doesn't make sense. Okay, you can't talk about the inverse for a non-square matrix. Now you can talk about things like right inverse and left inverse, but we're not going to get too into that. So, for example, I believe that this linear transformation does actually have a left inverse. So that would mean there's some matrix, and I'll tell you even how you might find that. There's some matrix that's going from R3 to R2. This is going from R2 to R3. That if you multiply it by this matrix, you should be able to get the identity. Okay. And how would you find this matrix? Well, just write A, B, C, D, E, F, multiply through all of these. So this will be telling you actually B plus 4C equals 1, etc. So I'll just say, so it's not defined, but this A does turn out to have a left inverse. But that's not good enough. Invertibility means we have to have a left inverse and a right inverse. Okay, so it's just kind of just a little aside. But yeah, this matrix does not have an inverse. Okay, it's not invertible. Okay, let's talk about... actually, I'll give you one case where we can find the inverse with very little calculation if we think about the linear transformation. So what's the inverse of this matrix? So this is not going to be a trick question again. I'm actually going to give you a square matrix. What's the inverse of this matrix? Oh, I should say, if it exists. If we have a square matrix, it still might not represent a one-to-one or onto transformation, right? So the inverse might not even exist. But if it does exist, yeah, what is the inverse? We have a chance for it to exist because we have a square matrix. Well, this represents, we saw something similar to this. So this is actually a 90-degree counterclockwise rotation. You might not recognize this just staring at the matrix. But over time, you'll get better and better at this. So especially if the matrix looks fairly simple, you can often interpret it as really nice linear transformation. So what's this doing? It's sending 1, 0 to 0, 1. That's what the first column is telling me. That's where this vector is going. So it's going there. And it's sending 0, 1. Where is that going? It's going to negative 1, 0. So it's going down there. Okay, so I end up with a vector here and a vector there. It's clear that this is sort of rotating two-dimensional space, 90 degrees counterclockwise. Well, the inverse, so the inverse should be what? Just think geometrically. Remember, I'm trying to reverse this and just get back to where I started. So the inverse should be a 90 degrees clockwise rotation, right? So let's write that down. So if I want to go clockwise, I just have to tell you where 1, 0 and 0, 1 are going. So here's my claim for A inverse. It should be, where should 1, 0 go? I want to rotate 90 degrees clockwise. So that should go to 0, minus 1. And then where should 0, 1 go? It should go here to 1, 0. So I think that's the inverse matrix of that. what you should try to do is multiply that one by that one and see if you get the identity. And you should. Okay. So I want to give you a formula for the inverse in a 2x2 case. Because before I do, actually, so really important. Not every transformation, or we're talking about matrices. So let's say, what would a transformation from R2 to R2 be? Will be represented by a matrix. So not every 2x2 matrix is invertible. Of course not, because we could have situations where we're not representing a one-to-one or onto transformation. So here's an example. Let's consider this matrix. I just want to try to think geometrically about what's happening here. So what is this telling me geometrically? Use a ruler actually, so it looks a little nicer. Okay, so where is 1, 0 getting sent? It's getting sent here to 2, 1. And where is, so that's going there, okay. And where is 0, 1 getting sent? It's getting sent in -4, -2. Okay, let me use a ruler again. That's down here. But you see these vectors are lying on the same line actually. So this actually causes everything to just get collapsed down. All of two-dimensional space just gets collapsed down to this line. Okay, this is sort of moving down there. This one's moving up there. All of two-dimensional space is getting collapsed to this line. Okay. You can think of that as every point is some combination of these two, some linear combination of these two. Okay. But where do these get sent? They both get sent onto this line. And so that linear combination also has to get sent to a linear combination of these two vectors, which will also lie in the line. That's what it means to be linear. This vector, for example, 3, 2, that's 3 times that plus 2 times that. So it'll get sent to 3 times this one plus 2 times that one. And that's actually this property here. And this one. I think we talked about sort of the meaning of these properties in the video on linear transformations. Yeah, so is this invertible? Is this transformation invertible? Well, no, you can kind of see that it can't, because all of two-dimensional space is getting collapsed down to a line. Now we can't take that one-dimensional line and then somehow, go back to two-dimensional space and have everything end up where it started. So this is not invertible. What's another way we can see that? These columns are clearly linearly dependent, right? So yeah, that's actually a really good way to see it. They're linearly dependent columns. And we have to be both one-to-one and onto in order for this transformation to have an inverse. And it turns out we're neither. We're neither one-to-one nor onto. Right, we miss everything except that line, so we're not onto either. Great, okay. Let's look at a formula. There's a formula. I'm not going to derive this formula because it's a little bit messy. There's a general formula. So the general formula exists for the inverse of well, in general, like any n by n matrix, but these formulas get very messy very quickly. So let's just do the 2x2 case. Here's what the formula is. So if my matrix is given by A, B, C, D, right? Because we can't always think geometrically. Like this example is pretty simple, where it corresponded to something really nice geometrically. Sometimes it won't correspond to something very nice geometrically, and then we want a formula for it. So if that's my matrix, then A inverse is given by this formula. So Actually, I'll write it like this. So it turns out everything has the same. So I'm going to write a matrix with fractions in it. But all these fractions have the same denominator, which is AD minus BC. So I'm going to factor out a scalar, 1 over AD minus BC. And then what it looks like is actually D, it's kind of strange, but D minus B minus C and an A, like that. Okay, so that's actually just a formula for the inverse. You should be free to use this, feel free to use this formula. So it only works for 2 by 2. Again, the formula gets much more complicated for 3 by 3 even. It's pretty complicated. And then for 4 by 4, you'll have a hard time even fitting it on a piece of paper. But wait a second. Okay, so why couldn't we have used this formula for this matrix, right? Can't we just plug this into the formula? Well, for the matrix above, what if we plug it in? This part is fine, but what is 1 over AD minus BC? That would be, so AD minus BC is 2 times negative 2, which is minus 4. And we have minus negative 4 times 1, which is another minus 4. So minus 4 plus 4, which is 0. We can't divide by 0, right? So this formula doesn't work. So this formula only works if AD minus BC is equal to 0. Okay? So assuming this, you can only find the inverse using this formula if AD minus BC is non-zero. Right? So we can divide by AD minus BC. This is something called the determinant, by the way. We're going to talk about that soon. So the determinant has to be non-zero in order to use this formula. And it turns out a matrix is going to be invertible exactly when its determinant is non-zero. Okay. But we'll get to that. I want to do a quick example just using this formula to show you how useful it is. So let's find the inverse of a matrix A, where A is 1, 3, negative 1, 2. Okay, what is A inverse? Well, let's just write down the answer. A inverse is 1 over AD minus BC. What's AD minus BC? So AD 2 minus BC minus negative 3. So 2 minus negative 3, which is 5. So 1 over 5 times D minus B minus negative 1, which is 1, minus C, A. So A inverse actually ends up having these fractions: 2/5, 1/5, minus 3/5, and 1/5. That is A inverse. That is the matrix. You can multiply by this matrix and get the identity. As you can see, geometrically, there's no way we would have been able to figure this out, right? Just by thinking about what this linear transformation does. Okay, let's talk about some properties of the inverse before we get to go too crazy with this. So properties of the inverse. So again, we can only take the inverse for square matrices: 2 by 2, 3 by 3, 4 by 4, etc. Let's try to make the first property something easy. So what happens if we take the inverse of a matrix and then the inverse of that? Maybe that's not so easy to think about. Well, what does this mean in terms of linear transformations? Right? So we're going from Rn to Rn. Have to be the same for the inverse to exist. Well, what would A inverse be? That would be the transformation going back, right? From this Rn to that Rn. Well, what if I take the inverse of that transformation? It's just flipped around again. It's the transformation going forward again. So A inverse inverse is just the same as A. If you take the inverse twice, you just get back what you started. So that's not really saying much. Oh, here's a more interesting one. So if AB, these are just two matrices, equals AC, A times B equals A times C, so just a quick review of the previous video. This does not mean that B equals C, right? And you maybe did that example in the previous video. However, if we know that A is invertible, if A has an inverse, then it is true that B equals C. Okay, so that's pretty cool. Well, why is that? We can actually prove it right here. So here's how you prove it. AB equals AC. So you can't just cancel out the A's. We talked about that. But here's what you can do. You can multiply both sides by A inverse. You can certainly multiply both sides of a matrix equation by anything you want, as long as it's the same thing. And then what you can do is switch to parentheses. That's because matrix multiplication is associative, right? You can group them however you want. You can't flip the order of A and C, for example, but you can group them however you want. And then what is A inverse times A? Well, what does A inverse mean? It's the matrix that you multiply by A to get the identity, right? So don't ever forget that. So A inverse times A is the identity. Similarly over here. But what is identity times B? That's just B. Identity times C is C. Okay, so we just proved that if A is invertible, then you can actually cancel a matrix. Okay, so that's pretty cool. 3. Oh, let's do a really important one. In fact, this is maybe the most important thing in the whole class. Let's say I have an equation, our favorite equation, A times vector x equals some vector b, which is a system of equations, for example. Okay, we can write a system of equations this way. So if we have a system of equations written in this form, matrix times a vector equals vector, and we know that A is invertible, which actually means it has to be square, right? So we have to have the same number of equations as variables. But you know, this kind of equation might not always have a solution, right? But it does if A is invertible. Why? You do the same trick. Multiply both sides of this equation by A inverse. They cancel on this side, and you just get, what do you get? You get x equals A inverse times B. That's cool. So that would be the solution to my equation, right? My system of equations. I'm going to put a box around this one. This one's very, very important. So if our matrix is invertible, the matrix sort of holding the coefficients to the system of equations, if that's invertible, then I can write down the solution. And you see it's a unique solution, right? Because it's just whatever the vector b is times its inverse. Inverses are unique also. That should be a property too. But yeah, so inverses are unique if they exist. And yeah, that's the solution to my system of equations. Let's do a quick example of this. So here's how to use this property. So let's solve the system. X minus y equals, say 4, and 3x plus 2y equals -1. Okay. Well, we have ways that we can solve that system. But here's a new way. Okay, let's write this in matrix form. So I have 1 minus 1, 3, 2 times my vector x, y. This is like my A, here's my vector x. And what is my b? It's 4 minus 1. Here's a solution. Yeah, here's the solution. xy equals A inverse times b. What is A inverse? Well, I chose the matrix we had above as the coefficients. You might have noticed that. So we already calculated the inverse. But in general, you would calculate the inverse here. So let's put that in. Here's A inverse times, I just multiply it by b. Okay, so let's multiply this out. So I can do it this way. So there's my first entry. It'll be 2/5 times 4, which is 8/5, minus 1/5, which is 7/5. That's my top entry. And this entry will be minus 3/5 times 4, minus 1/5, minus 13/5. So x equals 7/5, and y equals right over here. And y equals minus 13/5. This method for solving systems of equations is very important in practice. So it's just one multiplication you're doing. But you do have to find the inverse, which can get tricky if we have larger matrices. But let's do that next, actually. So how do you find the inverse of a 3×3 matrix, for example? Or actually, okay, before we do that, one more property that's just really cool. What if I have a product A times B, and I want to find the inverse of that product? That's actually the same as, so it's not true that it's A inverse times B inverse. It's actually B inverse times A inverse. That probably looks really weird. But this actually makes total sense. So why is this true? Oh, of course, we're assuming that these are invertible. Right? Otherwise, this formula doesn't make any sense. Okay, so why is this true? Well, if that's the inverse of that, then I should be able to multiply it, actually on either side, and get, actually, sorry, so I should be able to multiply by, if this is the inverse of AB, right, I should be able to do AB times this and get the identity. But you see that I do, right, because I can group them however I want. So it's just A times B inverse is I. But, A times I is just A, and then A times A inverse is the identity. Okay. But there's another way to think about this. So let me get a prop. Let me get my pack of cards again. So what if we do a rotation, 90-degree rotation, and then a horizontal flip? How do I reverse that? Do I do the 90-degree rotation backwards and then the horizontal flip backwards? No, right? I start by doing the horizontal flip backwards. And then I do the 90-degree rotation backwards. Right? So that's what this is saying. If I have, so B would be the rotation and then the flip. How do I reverse that? It's saying first I do the flip backwards and then I do the rotation backwards. Another example, this is kind of a cool example to think about. So what if I want to reverse the following transformation? So first I'm going to put on socks. And then I'm going to put on shoes. So what if I want to do the inverse of this? Well, first I have to take off the shoes, right? So I do shoes inverse. Then I have to take off the socks. Okay, so you see how they're in reverse order? So this actually makes total sense. You just have to think about it as transformations. Okay. Let's now talk about an algorithm for computing the inverse. So this is an algorithm for computing inverses. And let's stick with 3×3 for now, but this generalizes for larger matrices. So A1, A2, A3 will be my columns. Okay, so these are vectors, column vectors. But any 3×3 matrix. So yeah, let's let A be this. And if B is the inverse matrix, which I don't know yet, that's what I'm trying to find. Okay, so here's my inverse matrix. Well, if this is A inverse, then what should be true? Well, certainly if I multiply A by B, so matrix A, and I multiply it by B, what should I get? What should I get the identity? Well, what is the identity? It's 1s down the diagonal, 0s everywhere else. So that's the 3 by 3 identity. Okay. Now, here's the cool thing about this. So let's say I want to find this first column of my inverse matrix. Okay, I'm given these. I have no idea what this matrix B is. That's what I'm trying to find. Let's say I want to find the first column. Well, see, this matrix A times that first column just gets me this first column here. So, if I wanted to find B1, I would solve this augmented matrix. A1, A2, A3. Sorry, I did not mean to cut it off there. I meant to put a red line with, these are my variables, and I'm trying to get 1, 0, 0. Okay, so I would solve that. I would do Gaussian elimination until I get down to, so just some row operations. And let's say we go all the way to reduced row echelon form. And I get something over here. Okay, what is this here that I get? Well, that should be my vector B1. That's my solution. Right? Yeah, this is my solution to AX equals 1, 0, 0. But what is the solution to AX equals 1, 1, 0? This matrix times that vector equals that vector, so that has to be B1. So I'll just say which is B1, my first column. So that's how I can find the first column. I just do Gaussian elimination, and I put the vector 1, 0, 0 over there. And then to find the second column, I should do the same thing but with the vector 0, 1, 0 put in place there. And then to find the third column, I should do the same thing, but with the vector 0, 0, 1 put in place there. But that's tedious, right? We don't want to do all of that. So the idea is to do several Gaussian elimination problems at once. So we'll do several Gaussian eliminations at once. Let me just give you 3 steps. So first step is we form the matrix. This is like a super augmented matrix. So we'll have A1, A2, A3. Now on this side, we'll have, I want to solve it for this. I also want to solve it for this. And I also want to solve it for this. So I'm putting multiple columns on this side of the red line. It's something we haven't seen before. Step 2, I want to reduce the left-hand side to all the way to, we really want to go all the way to reduced row echelon form. And I also want to apply the same row operations to the right-hand side. Okay, so these numbers over here. Okay, step 3, when you're done, the left-hand side, I guess I abbreviated LHS, that should be turned into the identity. should be the identity. If it's not, then our matrix is not invertible to start with. And the right-hand side, what should that be? I'm sort of getting one column of my inverse matrix at a time. So the right-hand side should be, if we did it right, it should be the inverse that we're looking for. Okay. Let's do an example, so this is a little bit less abstract. So let's find A inverse, where A is the matrix. We'll do a 3 by 3. 1, 0, 1, 0, 1, minus 1. I tried to make one that works out somewhat nice. Minus 2, minus 1, 0. Okay. What do? I form the augmented matrix. I put my matrix A here, and then draw a line. And on the right side of this line, I put what? I put the identity. So this is the identity. Now I'm going to start doing row operations. I want to turn this into a reduced row echelon form. First thing I want to do is subtract the first row from the third. This will be a 2. What do I get on this side? Minus 1, 0, 1. Right. Next thing I want to do is eliminate that minus 1. So I want to add the second row to the third. 0, 0. This should be a 1 now. But see, I'm also doing it over here. So I need to add the second row to the third row. So I'm going to get minus 1, 1, 1. Okay. This is looking good. I have 3 pivots. If I did not have 3 pivots, let's point this out. So if we don't get a pivot in every row, what can we say? A is not invertible. Right? Because, these columns of A do not span, or they are not linearly independent. Those are equivalent, right, for a 3 by 3 matrix. And so if they don't span or aren't linearly independent, then the linear transformation associated with A cannot have an inverse. Okay, so we have to make sure we get a pivot in every row. Let's keep going. So what are we going to do next? Let's try to do 2 at once. So I'll write down my last row. My last row is good. I need to get rid of this minus 1 and minus 2 here. So I should get in the habit of writing my row operations, right? So row 2, I'm going to replace it with row 2 plus row 3. And row 1 I'm going to replace with, well, it's the old row 1 plus 2 copies of row 3. That'll cancel out that minus 2. I'm using row 3 to get rid of these. Okay, so let's do row 2 first. It's going to become 0, 1, 0. And then this middle row is going to become minus 1, 2, 1, right? Because I added row 3. Then the top row will become 1, 1, 0. But then this will become minus 1, 2, 2. Okay, I added 2 copies of row 3. And we're done. See, what we have here is the inverse, the identity. So what is this thing over here? Well, this is very exciting. This must be A inverse. Okay, very cool. So that's a little algorithm for finding the inverse. And, there's one last thing I want to do. I want to go to our unifying theorem. So before I do, actually, I just want to point out, let's do it down here. So let's say, if this matrix A, so if AX equals B has a solution, let's say a unique solution for every B And here A is a square matrix. Can't even talk about the inverse for non-square matrices. So if it has a unique solution for every B, well, what does that mean? Well, it means, first of all, that these columns will span and be linearly independent, and we can basically just use this method to calculate the inverse, right? Because these, in particular, it has a solution for these values of B, okay? And so we can always find, we can always just carry out the Gaussian elimination. This algorithm is actually the proof for why, this implies that the inverse should exist. So A has an inverse, or A is invertible. But this is actually one of those double arrows, because if A is invertible, what does that mean? If A is invertible, we can solve this, right? We just multiply by A inverse on the left, and that's our unique solution. So if A is invertible, that means we have a solution. This AX plus B has a unique solution for every B. Okay. So let's add that to our setup here. Okay, so here we have this equation AX equals B has a unique solution for every B. That's equivalent to A is invertible. And you see what we've just done is we've related this concept of A being invertible to a bunch of other concepts, and these will allow us to see. We can stare at a matrix sometimes and just see if it's invertible. For example, if the columns of that matrix are linearly dependent, A cannot be invertible, right? Because these are equivalent. Okay? Or if we have a transformation that's not one-to-one, then A cannot be invertible. But for example, if we have a transformation that's onto, A must be invertible. We must be able to reverse that transformation, which is crazy. That's just amazing, right? Just any linear transformation that's onto, we can actually find a transformation that goes the other way that completely reverses it. Okay. So this is really powerful. All of these are equivalent, and we're going to even start adding some more starting in the next lecture. Okay, so I've gone way over time, so I should stop now, but thank you for watching.